Hello all, welcome to today's webinar. We will be starting in couple of minutes. Hello all, welcome to today's webinar. Thank you for your time and we welcome you to today's webinar. Before we start the webinar, couple of housekeeping items. All of you are at present are on mute mode, listen only mode, and you will, if you have any questions, you can definitely type in the question panel and raise your hand. We will answer all your questions at the end of the webinar. So I welcome you all to today's webinar. Before I start, let me give you a brief introduction to Tridiagonal Solutions. We are a group of 100 plus R&D professionals, and we provide innovative solutions to our customer. And our mission is to create value by developing innovative solutions and support our customer throughout the product development. With a global experience of 12 plus years and having a team of 100 plus R&D professionals, we have delivered 800 plus projects and have successfully delivered 15 plus patents with about 15 plus applications for complex engineering, which helps the process engineer to use those applications and solve their problems with ease. We work with Fortune 100 clients, all multinational 100 plus clients, and we have a large testing facility for testing of flow in large oil and gas pipelines. With our experience in process consulting, process development, and optimization, we do concentrate on areas like mixing, spraying, coating, and powder mixing, and help our customer to solve their process problems and troubleshoot and help them to understand better, gain more insights, and troubleshoot their process problems. With our consulting experience, we have developed a few applications which are helping our customer to solve their process problems. And then we are developing new platforms which will help our customer to gain more knowledge based on data science from their processes. So this is a brief list of our customers. So with 12 plus years of experience providing most advanced technologies and solutions to our customer, we do help our customer, work with our customer hand in hand to provide them end-to-end solutions and provide them support and training through our consulting practices and make sure that we are able to solve their process problems and improve their process performance using innovative technologies. So with this brief introduction to today's to Tridiagonal, let me we will start on our webinar. I am Gopal Kasat. I am heading the Chemical Reactor Engineering Group at Tridiagonal Solutions. And today we will be discussing how we can handle the solids addition and suspension challenges in stir time. So what is solid liquid mixing? So when I think about it, like we do encounter it in our day-to-day life, when let's say we are adding sugar in water, and if we do not stir it with a spoon, then definitely the sugar is going to settle at the bottom. So that a simple example helps us to understand how important it is to suspend the solids in the process industry in our chemical processes so that maximum area is available and we get effective mass transfer and effective process control when we are dealing with solid liquid operations. So when we think about solid liquid mixing in process industry, we encounter various processes where solid liquid mixing is very important, like dissolution, where, like I said, we are dissolving sugar in water. That is a very simple example, but we encounter that in day to day in process industry. Along with dissolution, we have crystallization, where we need to control the particle size distribution, make sure that the crystals are suspended and we have the appropriate particle size distribution. Precipitation, suspension polymerization, for example, forming of resin beads, where we need to control the particle size of a resin bead. In terms of solid catalyzed reactions, there we need to suspend the solid so that maximum surface area of the catalyst is available for the reaction. In food and beverages industry, we do encounter powder dispersion in various food and beverage industry, and in bioreactor, definitely we need to suspend biomass, and there also we encounter the solid liquid mixing problem during in our day-to-day process industry. So what type of typical things we do in these problems? So either we are trying to suspend the settled solids, which are typically heavier solids, which tend to settle. We need to ensure that they are suspended, or we are trying to draw down the floating solids. Typically, the solids will be available at the are added at the surface, and we need to make sure that we are drawing them down and dispersing them properly in the mixing tank. So let's understand about suspension of settling solids. So typically with heavy solids, when we are dealing with heavy solids, the heavy solids tend to settle under the action of gravity. And in order to suspend the solids, the fluid velocities near the vessel bottom need to overcome the settling velocity of the solids. And typically the turbulent eddies generated because of the fluid action would lift the solids, and then the solids will be suspended in the bulk fluid using the bulk flow generated by the impeller. This is typically action we encounter in mixing tanks. And the critical design parameters are, we typically use a term called minimum suspension speed. That is the minimum speed at which the solids are suspended off the vessel bottoms. They may not be uniformly dispersed, but they are just suspended off the vessel bottom. And also in some cases, we need to ensure that solids are uniformly dispersed. So we are looking at level of suspension as well. And we can define the various level of suspension based on the type of processes we are dealing with. Either it could be a partial suspension where the solids are just suspended off the vessel bottom, or complete suspension where the solids are lifted off the vessel bottom and are dispersed in the bulk volume, as well as uniform suspension where we have solids concentration uniform in each and every region of the bulk fluid volume. So let's understand, as we see that settling solids, they settle under the action of gravity. Let's understand what happens with floating solids. So solids float due to density difference. The solids are lighter than liquid, hence they may float. some of the solids may have poor wettability, and also if we are adding them from the liquid surface, they may float. And even if we are adding the lumps of the solid, then because of the low density, those lumps of the solids may also float. So what is the action required to suspend or disperse these floated solids? So typically, due to the buoyancy and surface tension, the solids will float, and we need to overcome these forces using gravity, drag, and turbulent dispersion force, which is generated by impeller. So we need to overcome the surface tension and buoyancy force using the gravitational and drag force and turbulence force generated by impeller, so that the solids are being drawn down and then dispersed in the bulk liquid. Here, the two key parameters of interest are the NJD, which is like the NJS, which is just suspension speed. We have a term here called just drawdown speed, where the minimum speed where the solids are just drawn down of the liquid surface, and cloud depth, like cloud height or suspension height in case of suspending heavy solids. Here we call it cloud depth, where the solids, how much the solids are incorporated in the liquid from the liquid surface, that is where we define the cloud depth. And while we are dispersing these floating solids, vortex play a very critical role, and we need to ensure that we have a controlled vortex, so that due to the vortex there is a surface turbulence created, and that helps to disperse initial dispersion of solids, and then bulk motion of the fluid will disperse the solids in the bulk of the tank. So let's understand. So we understood what we need to do in terms of either suspending the solids or drawing down the floating solids and dispersing them. Now let's understand what are the typical design variables available which impacts or which we can change to make sure that we are able to suspend solids or we are able to disperse the floating solids properly. And these design variables are typical reactor hardware. So typical in case of suspension, when we are trying to suspend the settled solids, then definitely the bottom shape of the reactor will play a critical role. Then definitely what type of impeller we are using, its size, what type of impeller, its size, location, and number of impeller. There are various impeller available. Some are axial flow, some are radial flow, and some provides us mixed flow. So which type of impeller to be used is also one of the variable available to us, which we can change to make sure that we have better suspension. And one of the important parameter is baffle. So how we control the baffling so that we ensure enough suspension as well as enough drawdown of the solids. That is very critical in case of drawing down of solids. The baffling is very important. How we provide baffle and how we control the vortex by providing some partial baffles maybe helps us to improve the performance of a powder dispersion when the powders are light. So apart from this reactor hardware, there are operating conditions where we can control is what is the addition location we may add at the surface or inside the bulk liquid based on the flexibility of operation, or in some case we can control the particle size, so we can reduce the particle size so that the particles are dispersed properly, and maybe the surface tension of the particle, the surface tension or interfacial tension between the particle and liquid, and the wettability will play a critical role when we are either suspending the solids or dispersing them. So with this design variable, let's understand how we can ensure that our operation is, we are operating in a suitable regime, or the solids are suspended. What are the parameters which we can estimate to make sure that the process we are operating with the given operating parameter is able to suspend solids and disperse them uniformly. So for settling solids, where we need to suspend the settling solids, one of the critical parameter is estimation of minimum impeller speed for off-bottom suspension, and there have been various correlations available in literature, and one well-known correlation is the one proposed by Zvettering in 1958, where the critical impeller speed is calculated as a function of various parameters, like operating parameters, which is the particle size, density of the particle, density of the liquid, and the overall loading of the solids, and then the reactor hardware also incorporated in this correlation, which is the impeller diameter. However, when deriving this correlation, the all other parameters like either the effect of the impeller position or the effect of impeller to tank diameter ratio or the effect of vessel bottom shape was incorporated in this one single parameter, which we call the S factor. And to use this correlation effectively, we need to ensure that we have the right value of S factor so that we can estimate the right suspension speed and operate at that speed to make sure that the solids are suspended. And this correlation is developed based on visual observation of the vessel bottom, where what Zvetringas did is he tried to observe the vessel bottom and then ensure that and he recorded the speed at which no particle remains stationary on the vessel on the tank bottom for more than 1 or 2 seconds, and that speed he noted down as a critical or minimum impeller speed for solid suspension, and then correlated it with various operating and the reactor hardware parameter. Another correlation was proposed in 1978, where again the various parameters were incorporated, and in this case they also took into account the impeller to tank diameter ratio, as well as all other impacts were recorded in this one constant, which is the Z value. This equation was based on an energy balance, where the hypothesis was that the solids are suspended due to turbulent eddies, and these turbulent eddies would, at the vessel bottom, would help to lift the solids, and then the solids will be suspended using the bulk flow. Recently, in 2015, there was a correlation published by Professor Greenville, where again various parameters which were also in the earlier correlations were incorporated. Now here they have also incorporated the impact of impeller clearance or impeller location with respect to the impeller diameter, as well as the power number of impeller, and all other parameters were then incorporated in this constant Z. And this work was based on the work of Davis 1986, which describes that how particles are lifted, again based on the turbulent eddies, and this correlation was again backed by some experimental data as well. So these are few correlations which are generally used to calculate the minimum impeller speed for suspension of solids of the vessel bottom. There are many other correlations. I just picked these 3 correlations which are heavily used in general in the industry. In terms of suspending settling solids, there are also some design guidelines available which we can refer to. Like typically, while selecting the impeller, we need to ensure that it is an axial flow impeller or a mixed flow impeller with a impeller to tank diameter ratio less than 0.5. And why axial flow impeller? Because the axial flow of the impeller would hit the tank bottom and then would create a turbulence there, which will help to lift the solids better. There are also guidelines available in terms of what should be the clearance and what should be the spacing between the impeller if we are working on a multiple impeller system. Similarly, for baffles arrangement, 4 standard baffles are recommended when we are dealing with suspending the heavy solids of the vessel bottom, and what should be the dimensions of those baffle are also given in those recommendations. Then, as we discussed that there is a guideline on what should be the clearance of impeller from the vessel bottom. Now we can see there have been published literature where the impact of clearance on the critical impeller speed is clearly defined, where up to a certain clearance, the clearance of the impeller does not impact the overall suspension speed. However, as soon as we cross that value, which is almost 10% of the impeller diameter, then we enter into a region where if we move the impeller up from the vessel bottom, then we see an increase in the required suspension speed. And after, if we move the impeller up to 30% of the tank diameter from the vessel bottom, then there is a significant increase in the required speed to suspend the solids. And typically it is recommended that we stay in this second region to select our impeller clearance from the tank bottom. So there are guidelines available in case of settling solids. However, for minimum impeller speed for drawdown of the floating particles, there are few correlations available, but not much guidelines are available because very less study have been done on how to draw down the solids, floating solids in the bulk liquid. So the first correlation for minimum impeller speed for particle drawdown was published in 1977, where the particle density, a difference between the particle density and liquid density, and the impeller to tank diameter ratio was correlated, and then the constant was devised. And this correlation was based on some fixed system where single partial baffle with axial flow impeller was used, and the definition was there is no stagnant zone of floating particle at the liquid surface, and the particle are just started disappear from the liquid surface. That was the criteria to define the speed is the just drawdown speed. Another correlation was published in 1999, where again similar density difference between the solids and liquid, as well as the solids volume fraction and some other particle properties were used, and all other constants were grouped in this one constant, or all other impact were grouped in this one constant to estimate the just drawdown speed. So this was based on some experimental data with again 4 baffles and a Rushton turbine impeller. And then there are some general guidelines available in terms of how we can effectively draw down the in terms of controlling the vortex with partial baffle and the impeller of bottom clearance that we can control, so that to draw down the floating solids. And in general, as we have seen, there are guidelines available uh, to suspend the solids or to design a system for suspension of solids. Then there are very less guidelines available for drawdown of the floating solids. So there is very less literature available on how we can draw down the floating solids and disperse them. So let's try to understand how these empirical correlations can be used, or what could be the limitations of these empirical correlations. So we have seen that for suspension of floating solids, we have few equations. Then for drawdown of floating solids, we have few equations. And if we look at all these equations, these are heavily dependent on some constants, which are grouped in one of the parameter. For example, in case of Zwittering, we have S factor. In case of the equation proposed in 1978 by Professor Baldi, we have the power number. Similar power number is used in case of correlations proposed by Professor Greenwell, and also in case of particle drawdown speed estimation, then we have also constant. And these constants have been derived in this while proposing these correlations. However, they are for a very fixed system, as we discussed that some of the authors have used, or some of these published correlations have used the experimental data only for Rushton turbine or only for pitch blade impeller. So there are limitations in terms of these constants are available for all of the system, and we know that we encounter very non-standard configuration in our process industry. So how we can use these correlations with this non-standard system, because they are very system specific and they heavily depend upon an impeller constant like power number and some other factors which are dependent on the various vessel geometry and configuration of impeller. So with few limitations in these correlations, let's see how we can use few other technologies to ensure that we understand the solid suspension process better, or the solid dispersion process better, and improve our process performance by making sure that it is good. So with the computational fluid dynamics model, we can definitely use the computational fluid dynamics model to understand the performance of our process a priori, and do use those results for analysis, troubleshooting, and scale up. The computational fluid dynamics model provides us detailed understanding of the flow pattern, how the solids are getting suspended based on the flow pattern or the location of impeller. And we can make a judgment based on this. What is our suspension speed? We can estimate that, as well as we can understand if we need up bottom suspension, what should be the speed. If we need complete suspension, what should be the impeller speed. So we can use these detailed insights from the CFD model to gain to improve performance of our solid suspension and the dispersion processes. So let's try to understand using some case studies how we can make use of this computational fluid dynamics model to improve our process performance. And I will discuss some of the case studies where we have helped our customer through our consulting practices to help them gain more insights into their suspension processes, and then improve them by doing small changes in their systems. So first example is where we can understand how the baffling will impact the overall process of suspension and what could be the impact of baffles. Because if we look at the correlation for this system, the minimum speed for this system is 280 RPM. But again, that this minimum speed is derived at a condition where we have 4 baffles. Now, what if we operate at the same speed or maybe higher speed than that? Let's say 480 RPM, but we remove the baffles or change the baffle configuration. Let's try to understand, can we get detailed insight using the computational models on what is happening or how the suspension will get impacted when we change the baffle configuration. So when we have no baffle, we get a vortex in an unbaffled tank and see if the solids are suspending. The solids are initially settled at the bottom, and we see that because the solids are only revolving on the vessel bottom, few are getting suspended, but however, bulk of the solids are still settled on the vessel bottom. And why this is happening? Because in case of the unbaffled vessel, the flow is very rotational, and then because of this rotational flow, there is no actual motion of the solids, and solids get dispersed. However, it took bulk of the solids are settled below the impeller, and that's where we see that even if we are operating at a speed which is almost 1.5 to 2 times higher than the just suspension speed, we are not able to suspend the solids properly in the tank. With addition of bulk baffle, we do see that the solids get started dispersing properly, and there is an improvement. The number of solid particles which are resting on the vessel bottom have been reduced, and the pattern has also changed, where we see more particles are now suspended. And what has changed? We have added one baffle in the system, and with this one baffle, we can see how the flow pattern has changed. Now it is more axial. There is a rotational component to it, but now the flow is more axial. If you look at the overall flow pattern in the vessel, just addition of one baffle have added an axial component to the overall flow, and that has improved the solid suspension. Similarly, with addition of two baffle, we do see significant improvement. Now the solids are more suspension, and the solids are first swept to the vessel wall, and they are suspended from the vessel wall. There is some amount of solid still settled near the or below the impeller, which is the dead zone, and again we can relate it to flow pattern, and we see that now more axial component is there. The impeller flow is more directed towards the vessel bottom with addition of second baffle, and it helps in improving the suspension. Addition of third baffle will improve again the performance. We do see that more solids are getting suspended now, and we get more uniformity in the suspension. And this is again, the flow pattern is again more on the axial side than the rotational side. So now the axial component is increasing in the flow, and the rotational component is reducing. And at 4 baffle, we do see a very good suspension, and the flow is again more axial in terms of the overall flow pattern from the impeller. It is very more axial and help us to suspend the solids uniformly in the vessel overall vessel region. So this is how we can see that the suspension of solids is being impacted by the baffle configuration. Similarly, we have helped our customer to improve their drawdown process or understand them. So with 4 flat baffles, we can see that RCI impeller, how the solids which are added at the liquid surface get dispersed properly, having 4 flat baffles. However, if we only use one baffle, then we get a lot of rotational flow, and the powder which is added at the liquid surface will remain at the liquid surface, and small quantity of them will get drawn down along the uh, along the shaft, and there will be a lot of rotational flow. Similarly, if we even change the baffle, there would be, like typically we use dual baffle in case of a glass line vessel, then we do see that the similar rotational pattern is observed with the RCI impeller, and we may not get better dispersion of the powder which is added at the liquid surface. So overall, we see that there is a significant impact of baffle configuration on the solid suspension and dispersion process. Proper baffling is need to be ensured for efficient suspension and drawdown of the solids particle. We do see that the available correlation do not exclusively account for the impact of baffle, and hence we may get detailed insight using CFD simulation and understand the quality of suspension better and improve our process by providing a proper baffling. Second example is where we have helped our customer to estimate NJS to improve their process. It was a RCI impeller and with a very different baffles. These baffles are just very much off center, and there are 2 flat baffle, or they were some probes kind of thing which were incorporated in the vessel, and the vessel was operating at 320 RPM. The estimated suspension speed using Zwittering correlation with a S factor of about 5 to 5.5 for RCI impeller is about 308 RPM, and the operating speed was much above the just suspension speed, but still there was poor suspension observed. So we calculated the settling velocity and then observed that there is a settling velocity of solid particles, and then estimated the fluid velocities in the tank, and we do see that the fluid velocities near the impeller bottom or the impeller below the impeller are less than the settling velocities of the solids. And if we even calculate the upward velocities of the solids, which will lift the upper velocities of the liquid, which will lift the solids particle, then we do see that those are less than the settling velocity, and that this is the reason because of that we do see that the velocity near the tank bottom is not sufficient enough to suspend the solids because it is less than the settling velocity, and there is a dead zone formed below the impeller. Because of this, we do see that the solids keep on rotating around the impeller, around the vessel bottom only, and they are not suspended because of the dead zone below the impeller. And then we change in the impeller position as well as change in the impeller speed, we were able to mitigate this problem of solid suspension. So with the CFD analysis, we can definitely get more insights and understand what are the basic cause of not getting the proper suspension, and then mitigate those problems by doing the proper troubleshooting in terms of either impeller position or maybe change in impeller, or then locating the impeller at appropriate position and then rotating at appropriate speed. Third example is again based on troubleshooting, but this time the problem was impeller pumping direction. So a tank with bottom mounted impeller was being used for preparation of a pharmaceutical intermediate, and there was requirement that heavier solids with density higher than liquid, almost double of that liquid, are to be dispersed, are added at the liquid surface, and they need to be dispersed. The operation was observed, and the solids were observed to be settled very much at the vessel bottom and below the and near the impeller. For this operation, the up pumping direction of the impeller was selected because it was thought that with the up pumping direction, the solid suspension would be much better. So the pumping direction was selected, and then when we have try to understand what is the problem, then we see that because of the pumping direction, the solids are being accumulated near the vessel bottom even at a very high speed. When the speed was, when the direction was changed, even with a low speed of about half that was earlier operation speed, we are able to get good dispersion. So a small change in the impeller rotation direction help us to improve the overall process performance and help to improve the process performance and even reduce the overall operating cost, because now the speed is reduced by almost half. Similar troubleshooting was done in another operation where a pitch blade turbine was operated in a down pumping in a pumping mode, and at the given RPM there was a bulk of solids were below the impeller bottom. Now with changing the direction of the rotation, the solids were able to suspend properly, and we can see that if we do the quantification analysis of number of solid particles, we do see that earlier with a pumping mode, the heavy solids were there at the vessel bottom. Now with the down pumping mode, we get better suspension and the solids are much more lifted from the vessel bottom. So detailed insights using CFD is definitely helping to understand what is the problem, and small changes in the direction of rotation helps us to improve the overall process performance and get better results from our processes. Another example is of a multiple impeller system where the problem was to draw down of floating solids. The density of the solids was less than, so lighter solids were there, and these were kind of floats. So the particle size was taken as around 6 mm, and the solids were observed to be floating on the liquid surface even after increasing the speed. The impeller direction was up pumping. In this case, again, it was selected to ensure that the up pumping motion of the impeller will help to create a surface turbulence and draw down the solids. However, when we have studied the flow pattern, we do see that there is a recirculation loop created in the top region of the vessel, because the top impeller is much away from the liquid surface, and the analysis of flow pattern has revealed this secondary circulation loop, and because of this, the solids were just getting circulated around the top region of the tank and they were not getting dispersed properly in the rest of the tank region. So we suggested to change the clearance between the impeller, locate the impeller properly, and move the top impeller closer to the liquid surface. With this, we were able to get one single circulation loop, and this helped to understand to improve the overall dispersion of the particles and get better dispersion using just change in the location of the impeller. So in this case, change in impeller spacing helped to improve the overall flow pattern and improve the dispersion of solids from the liquid surface. So we can get various insights and troubleshoot the overall process problems and make sure that with small changes like changing the arranging proper baffle or changing the impeller pumping direction or having a proper location of the impeller, we can improve the process performance. However, we can use these CFD models to also estimate the NGS in case if we are not able to estimate because the correlations are not applicable to our system. So a couple of examples where we have estimated NGS using the CFD models and validated them against experimental data. So in one of the cases, experimentally the NGS was measured by using a FBRM probe where the solid concentration or number of particles near the liquid surface were monitored using a FBRM probe, and based on those number of particle and change in number of particle with impeller speed, the NGS or the suspension speed was decided. We devised a CFD method where the number of particles near the liquid surface were recorded with the RPM, with various RPM, and the simulations were done at various speeds as was done in the experimental method, and then number of particles in the top region of the tank were recorded and plotted against the impeller speed, and we do see that after a certain speed the number of particles, the slope of the curve change, and we do see very less change in the number of particles. That means the suspension has achieved, and after this, even if we increase the impeller speed, there may be little improvement in the suspension. So the measured speed of about 50 rpm match very well with the experimental measurement of about 48 RPM. So the method, we can see that the CFD models can be used to even estimate NJS in case where the correlations may or may not be applicable. We can do the quantitative analysis by measuring the number of particles or particle concentration in various regions of the tank, and then get the estimation properly for the critical impeller speed as well. Similar exercise was done to validate the model or to validate the methodology, where we use a literature from 2010 where axial impeller was used to prepare a suspension and study the quality of suspension. And then in this case the particles in the lowest bin or near the vessel bottom, the tank was divided into number of bins, and numerical simulations were performed using CFD model to understand the number of solids near in the different bins, and the particle in the lowest bin, which is near the vessel bottom, were recorded with impeller speed. And again, the change in the curve, the point at which the curve change or there is no change in number of particles near the vessel bottom, was recorded as NJS, and this recorded NJS was then compared very well with the experimental prediction. And then in this case we also validated this method with respect to changing the number of bins. What happens if we divide the tank in 10 bins, 20 bins or 40 bins? Again, we were able to get within plus minus 10% deviation. The predictions were very good, matching with the experimental prediction of 350 rpm. We were able to get around 360 and 380 rpm with our numerical method. So overall, solid liquid operations, including suspension and drawdown of solids, are commonly encountered in the process industries. Many design parameters impact the overall quality of suspension in case of heavy solids, or dispersion in case of floating solids. Empirical correlations, we have seen, they give us better insight, they give us estimation of the critical impeller speed. However, they heavily depends on some constants and which are derived for specific system. And if our systems are away from the specific system, which are general case in the process industry, then we face limitations. In those cases, we see that CFD analysis provides us detailed insight and help us to analyze and troubleshoot the our problems and scale up effectively. So to do the CFD analysis, we can use various CFD tools available. However, as a process engineer, we do see that learning CFD and spending time on doing this simulation could hamper our other operations, and we may not need to get very expertise in doing the CFD analysis. So at Tridiagonal, we have developed a software tool which we call Mixit. It is an enterprise mixing analysis tool which helps the process engineers to use both empirical correlations as well as the power of CFD to understand their process performance better by using the CFD models in a fully automated way. The CFD models are fully automated here, so the process engineers may not need to worry about learning CFD. They can do the CFD analysis at click of few buttons, and we support various impeller configurations and even correlations and different rheologies in Mixit software. So process engineer can use it effectively and understand their processes better using the detailed CFD model, and can use the power of CFD model to gain detailed insight into their process performance. So for the attendees today, as a contribution to the industry during this overall challenging period of COVID-19, we have came up with a 30-day free trial offer for all those who have attended this webinar. We will give you a 30-day free trial of Mixit, and for doing CFD analysis, we support doing CFD analysis on cloud. So you can install Mixit on your laptop and connect it with the cloud to perform the CFD analysis. And along with this, we will also provide a 2-hour training session to you and your team on basics of mixing sciences and how to use Mixit. In this 30-day trial period, we will work with you to solve a couple of challenging problems you are facing in your process and help you to mitigate them and understand how you can use Mixit, use this CFD models and the mixed tool effectively to understand your processes better. So thank you for your patience and listening to me. We are now open to take questions. So there is a question that sometimes it is desired a good suspension, but solid particles cannot be subjected to much shear. How to balance of suspension lever and shear rate? Yeah, typically, and is there a specific agitator type or use in this case? Yes, typically this shear sensitive material we encounter in the bioreactors, and even in case of crystallization we may not need to we may not want our solids to be impacted by shear, because if they get impacted by shear, then in case of bioreactors the enzymes will get deactivated or the biomass will get deactivated. For crystallization process the shear will impact the overall particle size distribution. So in that case we can design the use the low shear impeller, make sure that we use high flow impeller like hydrofoil impellers to ensure that we get better flow. However, at the same time, these impellers provide less shear, so we can use appropriate impeller configuration to mitigate these problems. Second question is how you would you optimize impeller design at plant scale? Typical, this can be done by understanding the lab scale process better and the quality of suspension at lab scale better, and then we can optimize the design at plant scale. In some of the cases, we may not be able to, may be allowed to change the impeller or may not be able to change the impeller. Then we can change the impeller position or maybe try to incorporate proper baffle to optimize the overall performance and improve the suspension process. Another question is, can we get the effect of solid loading on power consumption? Yes, definitely. With the increase in the density, we can see the overall increase in the power consumption. So if we incorporate appropriate parameters in the simulation, we can get the effect of change in solid loading on the overall power consumption of the system. So thank you for your time, and do let us know your feedback on the webinar. One more question is there. How do you design small scale experiment to mimic the large scale? So typically to design a small scale experiment or scale down, we can understand uh, we may not be able to do a lot of experiment on the large scale, but what we can do is we can simulate that large scale process using CFD model, understand the quality of suspension, and then design a lab scale process to get similar suspension, and so that we can perform a lot of experiment at lab scale and gain better insight into our process. One more question is, how about the solids that are being formed in the liquid phase, like crystallization, precipitation? Does the model can be used to predict the size of the crystals and particle size distribution? Yes, the models could be used based on the level of turbulence and level of shear in the overall bulk liquid volume. We can relate them to the particle size and the particle size distribution. Another question is it possible to get entire reactors or impellers on group level in Mixit? Yes, we can have the entire database of reactors and impellers in Mixit as a database, and that database can be completely shared among multiple users. Another question is, if we are adding the solids which are lighter than liquid in reactor in semi-batch manner, which type of impeller is preferred for uniform suspension? Typically, in this case, we recommend to use down pumping impeller so that with the addition of solids, the flow patterns are not impacted, and again, we get better suspension and better flow pattern. Does the software provides values for various parameters? Yes, the software provides estimation. All these examples which I've shared with you were analyzed using Mixit software. So the software provides you detailed analysis as well as parameters such as shear, mixing time, suspension speed, and all other parameters using both correlations and detailed CFD models. Another question is, any best combination for a multi-purpose reactor? Yes, we can use typical axial flow impeller for multi-purpose reactors, where we can make sure that the flow patterns are good, as well as they help in suspending and dispersion of the floating solids. So thank you for all your questions. If there are more questions, please submit them and then we will get back to you with detailed answer on those questions. Thank you all for your time. Have a